Hello and welcome back. So you might remember that we got into this mess of describing data types because we saw that we couldn't construct the free monad on an arbitrary functor, which led us to consider a certain class of well-behaved functors. But what's the connection between this and the data type of data types that we constructed so far, right? So we had this desk, and then we had a way of decoding it as an operation from set to set, and we could take the data type that it represents. But if we try to get back to this idea of free monads, then we see that here, suspiciously, we have an operation from set to set, right? So that looks like the object part of a functor from set to set. So question is, a question which is prematurely answered by the title section, is if we can extend this to also be a functor. So that means that we need to have an action on objects, on objects which we have, and an action on morphisms, and then it has to preserve identities and composition. Right. So let's see if we can do this. Okay, so how would we do it? Well, we have to pattern match on the D, right? It's the old why is it stuck again? And the reason this is stuck is that we don't know what the D is, so we don't know what this little x is. But if we pattern match on the D, we're going to get these 4 cases. Like that. And now here, if D is backtick top, then we know that X lives in top and we need to produce something in top. So we can just get back the same X. And here, if we're dealing with a sigma type, then we know that this X comes from a sigma type. So it's some X comma Y. And we have to produce something in this sigma type. It's going to be a pair of two things. Here we need an element of A, but we have X, so we can keep the same X. And here we need something in the args bx of y, but we have something in the same thing of x, so we can do a recursive call. Okay, what about this one? Here we have a pair of things again, but this time they are both recursive things, but we still have to produce a pair of things. Okay, so we can just do this recursively, right? Like that. And what about this one finally? So here we have to produce a y and we have an x, but we have a function from x to y. So this is where we finally reduce the function, right? This is the recursive occurrence. So all the other cases are just that we can get down to this case. Okay, should we try to prove that this is preserving identities as well? Maybe we could even try to prove that this is a functor. We get a functor for every description. Right. Okay, so we know what the object part is, we know what the fmap part is. Now we just need to prove it preserves identities and composition. And how would we prove this? Well, this is an equation between functions, so we better use function extensionality, otherwise we don't know how to do it. And now we just need to prove this thing, right? Okay, and I know that I'm not going to be able to prove this directly. I have to do it by induction on the description. So I'll just introduce that as something I can pattern match immediately. Let's see that it's fit for purpose first. Yes, it is. Okay, pattern match on D. And we see that we get a bunch of cases. Okay, in this case, it's easy. In this case, it was defined like this. So we see that it's, well, let's see, so this x is really an x and a y. And the first components are already equal, so we use a cong. And down here, it's a straightforward recursive call. Here we also have a pair of an x and a y. And again, it's going to be a cong, this time a cong of 2 components and 2 recursive calls. And here finally we just get ref up. So that was easy. Let's do this one. It's going to be the same kind of thing. So we have to show something like this. Okay, so this time we have an x and a y and a z. We have an f from x to y, and a g from to z, and we have a d. Okay, does it work? Yes, it does. Okay, and again, all of this is stuck because of the D. That's what this is pattern matching on. So we do the same. Okay, so I'm just setting everything up to be as it was up above. And here we see that we get an easy goal. Here, the first components are again the same. And the rest is an recursive call. Here we again want an equation between pairs, so that's a com2. And 2 recursive calls. And here again we are lucky. Right, so we could actually make a functor. So now it makes sense to ask the question, is there a free monad on this functor? Are we so lucky?